In previous lessons, we mentioned that the only programming language that computers are able to understand directly is binary, which is a bunch of ones and zeros. So imagine if every time that we needed to instruct a computer to do something as programmers, we had to write programs written in this binary. In other words, as a programmer, for each instruction, we'd need to know the corresponding sequence of ones and zeros. That would get tedious very, very quickly. So that's why we're thankful for high-level programming languages like C, C++, Java, Python, PHP, which allow us to give computers instructions in languages that we are better able to understand. High-level programming languages. The purpose of today's lesson is to help us gain an appreciation of high-level programming languages and to help us see just how complex and borderline impossible for many of us programming would be without them. To this end, let's consider a very simple calculation. Let's say, for instance, we wanted to calculate the value of x given that the equation for x is a plus b minus c. Now imagine that we wanted to write a computer program that did this calculation. We'd probably think, well, it should be a simple program, a plus b minus c. How complex could that be, right? Well, not as straightforward as far as machine code or the code of zeros and ones is concerned. To explore why we say so, let's just cover a few concepts so that we can better understand this point well. Let's consider the computer's RAM and CPU. The RAM, as we mentioned in a previous lesson, stores all programs that are currently being run. In other words, if you're playing a game or working on a Word document with Microsoft Word open, whatever the case may be, all programs that are currently running are stored in the computer's RAM. The CPU, or the central processing unit, is the part of a computer that actually executes the program. The CPU has its own memory in the form of registers, and for the sake of our example, registers is what we're going to focus on as far as the CPU is concerned. So registers can be simply considered as the CPU's memory where it stores values that it's currently working on. So to be clear, RAM stores the entire program that's currently active. The CPU is what actually executes each and every command of the programs that are currently active. And the CPU uses registers as its form of storage, where it stores values that it's currently executing and the results from those executions. So with that in mind, let's go back to our example. X is equal to a plus b minus c. It'll be a good time for us, by the way, to mention this. Each computer has its own instruction set. What this means is that you cannot simply write a bunch of zeros and ones that are designed for one computer and then think that they are going to just work straightforward on another computer. Because, for instance, 0001 in one computer may be the instruction that represents add or addition, whereas 0001 in another computer may be the instruction that represents subtraction. So to this end, in our example, we're not going to be using any specific computer, but we're going to be using our own hypothetical computer with its own hypothetical instruction set. Let's look at some of our computer's instructions. The first instruction we'll look into is the instruction move, which has the binary code 0001. It's used to copy a value from the computer's RAM into a particular register in the CPU. An example of this instruction would look something like this: 0001 0000000001, which would mean move. So the first 4 bits, that's 0001, would be the actual instruction, which in this case is move. Move into registry 1. In other words, move into the CPU's registry, not registry 1, registry 0. Move into the CPU's registry 0, whatever is in the RAM's location 0000001. So in other words, this instruction would take whatever is in the RAM's location, which is 0000001 or simply 1. It would take whatever value is in there and move it into registry 0. And again, in binary, that instruction for our particular computer would be 0001 0000000001. Let's look at our next instruction. Add, used to add values in 2 registers and storing the result in a 3rd register. Instruction binary code for this is 0010. And by the way, 0010 or simply 10 is binary's equivalent of the number 2. So what would an instruction or add instruction look like? it looks something like this: 0010, 0000, 0001, 0010, which would mean the first 4 bits, or the first nibble, if you remember from previous lesson, represents the command, which in this case is add. Add value in registry 0 to value in registry 1 and store the result in registry 2, or in binary 0010. So that's what the instruction will be: add whatever is in registry 0 to whatever is in registry 1 and store the result in registry 2. And in binary, that instruction would look like 0010, 0000, 0001, 0010. Let's move to our next instruction. Sub or subtract, used to subtract the value in one register from the value in another register and stores the result in a third register. The instruction's binary code is 0011, and again 0011 is the binary version of the number 3. So an example would look something like 0011, 0000, 0001, 0010, which would mean subtract the value in registry 0 from the value in registry 1 and store the result in registry 2. Now let's consider our final instruction. Store, used to store a value to RAM from a particular register of the CPU. Instruction's binary code is 0100, and 0100 is the binary version of the number 4. So an example of an instruction, of a store instruction, would look something like this: 0100, which is the instruction, 0010, 0000, 0011, which would mean store again with the 0100, or the first 4 bits in our computer representing the instruction. So store the value in registry 2 into the RAM's location 00000011, or simply into location 3. So let's go back to our equation. We want to write a program that does this equation. So let's say, for the sake of our example, A represents the RAM's memory location 0, B the location 1, C the location 2, X the location 3. So what would our program look like written in binary or in machine code? Well, it looks something like this. First of all, we would say move into registry 0, A. That's what the binary stands for. Remember, 001 is the command move, and then the next 4 bits represents the registry, in this case 0. And then the next 8 bits represents the address, which is 0000, 0000, which, as we said, maps to A. Then next, we move into registry 1, B. Next, we move into registry 2, C. Then we say add the values in registry 0 and 1, and then store the result in registry 3. Then we say subtract the value in registry 2, which is, remember, C, from the value in registry 3, which is what we just added in the previous command, and store the result in registry 4. And then finally, store whatever is in registry 4 back into address 00000011, or remember that maps to X. In other words, in order for us to be able to execute the command X is equal to A plus B minus C, the binary equivalent, or the program in binary to do this, is these 6 commands. That's quite a lot for such a simple instruction. Now, of course, as humans, we don't generally think in zeros and ones. It was for this reason why the second generation of programming languages, generally speaking called assembly languages, came into existence. What do assembly language instructions look like? Well, pretty much what we were writing along to help us better understand what this binary means. In other words, the second generation of programming languages moved away from the zeros and ones. So now programmers could write programs written in symbols instead of zeros and ones, and words that made a little bit more sense and were easier to remember, such as move, add, subtract, store, etc. So when a programmer would write a program in assembly, there would of course be a need for that program to be translated back into machine code that the computer understands. And to do this, an assembler would be used. An assembler is simply a software or piece of code that's responsible for taking assembly code or a program written in assembly and translating those assembly instructions back into machine code. Now, assembly programming languages are still low-level languages. And by the way, low-level languages are languages that are very close to the computer's hardware. In other words, their hardware is very, very close to either understanding them directly or just a little bit of translation needs to take place in order for the machine to understand it. The reason why assembly languages are considered low-level programming languages, amongst other things, is due to the fact that when you write a program in assembly, you are still writing for a particular machine. In other words, you can't write program in assembly for this machine and then think that you can take the same program and go have it work in another machine. Because after all, you'll notice that for each assembly instruction, there is typically a corresponding instruction in machine code. So in other words, there is, generally speaking, a 1:1 relationship between one instruction in assembly for that particular machine and the corresponding instruction in machine code for that particular machine. I think we can all agree that from the perspective of the programmer, assembly code is much, much better than machine code from the perspective of the programmer who has to write programs. Because as we said, humans do not think in zeros and ones. Things like move, add, subtract, store, those are instructions that a human being can remember more easily and can be able to write programs much faster and more efficiently. But even though that's the case, assembly code is still not the best that we can do because, as we said, it's still quite close to the machine. You still have to remember registers, you have to remember a bunch of things that are, well, more close to the machine. So because of this, that's why the third generation of programming languages came into the scene, high-level programming languages. Now, as you can see, a high-level programming language now is even much closer to what a human is used to. To write a program that fulfills the task that we set from the beginning, x is equal to a plus b minus c. So to write a program that does this calculation in a high-level language, you would literally simply write your line of code as, well, x is equal to a plus b minus c. You see the improvement? So instead of those 6 lines of code, whether in machine or the slightly improved version of assembly, instead of those 6 lines of code, you simply have 1 line of code, which is pretty much exactly what you want it to do. X is equal to a plus b minus c. Now, of course, as is the case with assembly, the computer does not directly understand high-level programming languages or high-level code. So in order for the computer to be able to understand what the programmer's instruction is, a program called a compiler or another one called an interpreter, either of these is responsible for translating the high-level code into machine code that the computer is able to execute directly. So do we now see why high-level programming languages are important? Imagine if it takes 6 lines of machine code to write a simple program such as x is equal to a plus b minus c. How many lines of code would it take to write in machine code to write a program like, let's say, Super Mario or Photoshop and whatever complex program? It would be tedious. It would take too long. So that's why we're thankful for high-level programming languages, which makes programming much, much simpler. And that brings us to the end of today's lesson. Please don't forget to like, share, and subscribe. Do not forget to subscribe so that you do not miss subsequent lessons. Over and out. Let me give you a few seconds to subscribe. Are you done? You done? Okay, cool.